So, have you ever been deep into a really complex multi-step project, maybe researching a massive trip or compiling a huge report for work, and suddenly you just forget a crucial detail that you literally found 3 hours ago?
Oh, absolutely. It's like your brain just runs out of RAM.
Exactly. Your brain just hits a wall. And welcome to today's deep dive, by the way. We are looking at something super fascinating today because large language model agents, AI agents, experience that exact same goldfish memory problem.
They really do.
Yeah.
And it all comes down to this concept of a fixed context window.
Right. And as these agents perform long tasks, reasoning, acting, observing over and over, their path or their trajectory just grows linearly.
Until they literally run out of space to remember what they're even doing.
Which is wild.
Uh,
So our mission for this deep dive is to explore a state-of-the-art foundational paper. It's called ACE, Pluggable Adaptive Context Elasticizer Across Agents.
Quite a mouthful, but the technology is brilliant.
It really is. We are going to see how this paper solves the whole AI goldfish memory problem without permanently deleting a single piece of data.
Which is the key. It makes these AI agents vastly more reliable for the complex, hours-long tasks you actually want them to do.
But, before we can appreciate the brilliance of this ACE solution, we need to understand exactly how current AI agents are failing when tasks get too long.
Right. We need to look at why the current band-aids just aren't working.
So what's actually happening under the hood?
Well, in classic agent paradigms, like React, the agent operates in a continuous loop. It reasons about the state of the task, it calls a tool, gets an observation back, and then appends all of this verbatim to its memory.
Verbatim, so just copying and pasting everything into its brain.
Exactly. But as tasks get complex, this causes the information density to just plummet. The model's attention disperses across tons of redundant text, and its reasoning degrades.
Okay, let's unpack this. The paper highlights two main fixes that the industry uses right now, right? Truncation and summarization.
Yeah, those are the two big ones.
Truncation is basically just a sliding window. It's like cleaning your workspace by simply swiping everything older than an hour right into the trash can.
It's so aggressive. It just deletes older steps completely.
And then summarization or compression, um, that's like reading a dense legal contract, writing a one-sentence sticky note about it, and then burning the contract.
That is a perfect analogy. You are rewriting raw history into a shorter form, like a fixed-size memory state.
Which seems so risky.
It is. What's fascinating here is that both of these methods share a fatal flaw. They are completely inflexible and irreversible.
Irreversible, because once you burn the contract, it's gone.
Exactly. Once an agent drops or compresses a step, that original raw data is gone forever.
So if a seemingly irrelevant detail from, say, step 2 suddenly becomes critical way down the line at step 45.
The agent is out of luck, it can't recover it, and the entire task fails.
Wow. So since throwing data away permanently is clearly a massive disaster, how do we keep all the information without just overflowing the AI's limited context window?
Well, the researchers had a breakthrough. They realized that storage and working memory shouldn't actually be the same thing.
Which makes sense. Here's where it gets really interesting with the ACE architecture. It splits memory into two distinct layers.
Right. The first one is the message maintenance layer.
And this layer is entirely lossless.
Completely lossless. For every single step the agent takes, this layer permanently stores both the raw messages, so the exact reasoning, action, and observation, and it also stores a compressed abstraction.
Okay, wait, who writes the abstraction?
It's generated by an auxiliary LLM, something like GPT-4o, and this LLM explicitly saves critical facts.
Oh, like what kind of facts?
Things like URLs, specific numbers, causes of failure, and tool schemas. This is not just a vague summary, it's a highly targeted extraction.
I love this. It's basically like having a massive, perfectly organized filing cabinet down in the basement. That's the maintenance layer.
Yes, exactly.
You never throw anything away down there, but you only bring the exact specific folders you need right now up to your small desk. And the desk is the second layer, the context orchestration layer.
If we connect this to the bigger picture, it creates total reversibility because the basement never deletes anything.
Right.
A step that the AI thought was useless yesterday can be instantly recalled in its full, raw detail today if the evolving task suddenly requires it.
So I have this lossless basement and this limited desk. But practically speaking, how exactly does ACE decide what goes onto the desk at every single decision step?
That is where the Elasticizer comes in.
The Elasticizer, and that's another LLM, right?
It is. At each step, The Elasticizer looks at the task description and the abstractions of all historical steps.
Okay.
Then it tags every single past step with one of 3 labels. The first label is raw.
So if it's tagged raw, that means it brings the full original data up to the desk.
Exactly. It uses that for specific details or justifications that the agent needs right this very second.
Got it. And the second label?
The second label is abstract. That means bring just the summary up to the desk. This is usually for transitional context, just to remember what happened generally.
Okay. And the third label is drop.
Right. Drop means leave it in the basement entirely. It's irrelevant or superseded info.
But wait, I have to push back here. If the AI has to constantly read 50 past steps just to decide what to do with them, doesn't that process itself just eat up the context window?
You'd think so, but the paper has a really clever workaround for that. The Elasticizer only reads the short abstractions to make its sorting decision.
Oh, so it doesn't read the raw data to sort it?
Never.
Yeah.
That keeps its own input lengths tiny while still giving it full visibility of the entire history.
That is so smart. It's like reading the index cards to decide which textbooks to pull off the shelf.
Precisely. And there are strict boundary rules, too.
Like guardrails.
Yeah, guardrails. First, the original task description is always kept at the top, so the agent literally cannot forget its ultimate goal.
That's probably pretty important for these AI agents.
Very important. And the second rule is that the very last step is always kept raw, regardless of what the Elasticizer thinks.
Always. Okay, so a theoretical filing system is great, right?
Yeah.
But does it actually help AI agents succeed in the real world? And how hard is it to install this thing?
That's the best part. ACE is designed as an external wrapper. It requires absolutely zero extra training.
Wait, really? Zero?
Zero. It doesn't change the underlying agent's architecture at all. It is truly plug and play.
That's amazing. So what did they test it on?
The researchers attached ACE to 4 highly diverse agent frameworks. They used React, Deep Agent, WebThinker, and MiroFlow.
Okay, and what kind of models were they using to power those?
They use powerful models like GPT 4.1 and Gemini 3.1 Flashlight Preview, and they ran them on really tough benchmarks.
Like GIIA, HLE, and WebShop. Those are brutal tests. So how did ACE do against the baseline methods?
It consistently crushed truncation and summarization.
Can we have the numbers on that?
Yeah, let's look at the GAIA benchmark using Gemini. So Vanilla React, which just writes everything down forever, scored a 46.1.
Okay, 46.1.
Then they tried truncation, and the score actually dropped to 43.0.
Oh, wow. So deleting the history made it actively worse.
Way worse.
Yeah.
But then adding ACE skyrocketed the score up to 52.7.
That is a huge jump. So what does this all mean? Like, why should the learner listening right now care that this works on something called MiroFlow or Deep Agent?
It matters because of the broader implication, since it requires no training and works across single agent, multi-agent, and main auxiliary topologies.
It's basically a universal architecture agnostic upgrade.
Exactly. If you rely on AI tools for web research, data analysis, or coding, this is the technology that will stop them from confidently hallucinating or crashing when a task takes 50 steps instead of just 5.
That is going to save so many people so many headaches.
Oh, definitely.
But, you might be wondering if every single piece of this complex sorting system is strictly necessary. Like, do we really need all these gears?
And that's why the researchers did ablation studies. That's where you selectively turn off parts of ACE to see what breaks.
I love ablation studies. So what if the AI only had 2 choices instead of 3?
Right, let's look at that. If you only allow raw and drop, it acts way too much like standard truncation and ends up losing vertex details.
Okay. What if you only allow abstract and drop?
That one is terrible. The agent is totally starved of specific details, and it gets the lowest performance.
Because it only ever gets to read the sticky notes, basically.
Exactly. And finally, if you only allow raw and abstract, the context window just gets completely clogged with redundant task-irrelevant data, which drags down the scores.
So you absolutely must have all 3 gears: raw, abstract, and drop.
You really do. And they also tested that boundary rule we talked about earlier.
The one about always keeping the very last step raw.
Yeah.
Okay.
When they let the AI choose to abstract or drop its immediate past step, performance tanked.
Like how much?
The GIIA score fell from 52.7 down to 49.1 with Gemini.
Wow. Just from dropping the very last thing it did.
Yeah. This raises an important question about how closely this mirrors human cognition.
Right, because if I walk into a room and forget what I just did a second ago, I'm completely lost.
Exactly. Just like us, if an AI agent loses its immediate short-term memory of the exact thing it did a second ago, it loses its train of thought and gets completely disoriented.
That makes total sense. So, to wrap up today's deep dive, ACE, the Adaptive Context Elasticizer, it basically solves the dreaded AI context bottleneck by decoupling storage from active working memory.
By losslessly storing everything in the basement, but elastically shifting what the AI sees on its desk between raw, abstract, or drop states.
Which just makes long horizon agents vastly more capable and reliable. Such a cool concept.
It really is a game changer for the industry.
But before we go, I want to leave you with a final unmentioned implication to chew on. We've now given a single AI a perfect, flexible working memory for long digital tasks.
Right.
But what happens when we unleash swarms of these agents to work together over weeks or months?
Oh, that is a wild thought.
Right. If every agent has an ACE memory that can endlessly expand and compress its own perspective, how will these AIs negotiate whose raw realities and whose abstracted summaries are most important when they're collaborating on a massive, real-world human problem?
That is going to be incredibly complex to figure out.
It definitely is. Thank you so much for joining us on this deep dive. Keep questioning, keep exploring, and we'll see you next time.